Hello, my name is Andrew, and this is my lab video for the Black Hole Lab for Physics 2211. This lab had two parts to it. In part 1, I used a computational model to determine the unknown mass of a black hole in a system with a star that has a known mass. The system was the star, and the surroundings were the black hole and space. In part 2, I used a similar computational model to fly a ship as close to the black hole without crashing on the planet or into the black hole. The system was the ship and planet, and the surroundings were the black hole and space. The purpose was to show how momentum and gravitational force act on an object in orbit, and to show how the parallel and perpendicular components of force and momentum affect motion. The main results are shown below and will be explained in detail later. These are the formulas used in the computational model. The parallel change in momentum over time is equal to the change in the magnitude of momentum times p hat over time, where p hat is parallel to the direction of motion. The gravitational force formula can be modified as such to isolate one of the two masses. This will be useful for finding the unknown mass of the black hole. Newton's second law states that the net force is equal to the change in momentum over time and gives us the velocity and position update formulas. The initial conditions of the computational model include the star mass of 2 times 10 to the 30th kilograms. The black hole position is the origin, and the star position is randomly generated using the characters in my email address. And delta t is 1 day, which is equal to 86,400 seconds. We use the formula momentum equals mass times velocity to determine the initial and final momentum. We use Newton's second law to determine F net equals dp times dt. We rearrange net force equals net force parallel plus net force perpendicular to determine the perpendicular net force. And we use the rearranged gravitational force formula to determine the mass of the black hole. This video shows the elliptical orbit around the black hole that the star takes. It is calculating the mass values at each time interval. I took these masses and made an average of them and got the value 8.9 times 10 to the 33rd kilograms. The star takes an elliptical orbit around the black hole. The perpendicular force acting on the star pulls it towards the black hole. The parallel force keeps the star moving parallel to its current momentum. The further the star is from the black hole, the smaller the F net is, as seen by the arrows increasing in size as the star gets closer to the black hole. A possible source of error is that the mass values are rounded, so there is some uncertainty about the mass of the black hole. Moving on to the Part 2 computational model, I used the black hole mass from Part 1. The mass of the planet and ship are given. The speed ship is determined by trial and error, by me trying to get the ship as close to the black hole as possible without crashing onto the black hole or the planet. Since there's two objects in the system, the planet and the ship, I had to find the forces acting on both the planet and the ship, which is done through the process shown. The velocities are determined by the velocity update formula, and the positions are determined by the position update formula, as shown. This video shows the route taken by the ship to get as close to the black hole as possible. In order for this to happen, the initial velocity has to be negative 3.25 times 10 to the 7th for the x component and 1.33 times 10 to the 6th for the y component. The ship's path is magenta and the planet's path is cyan. The negative x component and positive y component of the initial velocity means that the ship initially heads to the left and above the black hole. As the ship gets closer to the black hole, the gravitational force acting on the ship due to the black hole increases exponentially. This force causes the ship to make a sharp left turn, but not be consumed because the ship has enough momentum to prevent itself from being pulled into the black hole. A possible source of error is that the masses that were rounded in Part 1 determine the mass of the black hole, and that mass impacts the gravitational force of the black hole, which has an impact on the initial velocity needed to get as close as possible to the black hole. F net is equal to the change in velocity, and F net parallel is equal to the parallel change in velocity. However, the change in momentum can be used in Part 1 to find F net, but F net can't be used to find change in momentum. This is because we tracked velocity and we're given the mass of the star, the two components of momentum, but we're not given all the aspects needed to determine F net. If the ship just wanted to orbit the black hole, It could have done so by increasing the y component of the velocity and decreasing the x component. In the code, I lowered the x component of the speed by a factor of 100 and the y component by a factor of 6, which resulted in a path that looked like this. Where cyan is the planet and magenta is the ship. Thank you for watching.